Hey everybody, hope you're all doing well. I'm going to go over some review of um, centripetal acceleration, uniform circular motion. Little quiz slash test out of 20, just one page front and back. I'll hand it out on Monday, 3 p.m. And you can get it back to me on Tuesday. Just take some pictures of the pages on your phone or whatever you're going to do, and find a way to get it to me if you want me to mark it for you. Okay. I think that your marks can't be negatively impacted from what they were before the March break. So if you do really bad on this quiz, it can't take away from your midterm mark, which is due next week, that I have to submit anyways. So your midterm marks are on the Google Classroom. Hopefully you saw those. I just dropped your worst test. And yeah, let's take up these questions. The first question says, it's number 22 on page 141. And it says you are operating a remote control car around a circular path in an open field. This is just one of those fill in the blank kind of questions where they give you centripetal acceleration, and it's about 3 times that of gravity, 33 meters per second squared. And they tell you the radius of the track, which is, this must be a pretty crazy remote control car track here. And you need to find the speed. Well, easy enough. You just let ACP equal V squared over R and solve for V, right? V will equal the square root of AR. And you know your numbers, so you solve it. It's really quite that easy. That's like a grade 9 question for you. Okay. And there'll be something like that on the quiz, I'm sure. So just kind of straightforward to make sure you understand the real basics. The test is not going to be hard by any means. Okay. Just meant to so that you're not completely lost if this whole semester gets scrapped or whatever, that when you go to university next year and you take a physics course, then you will at least have something in your memory bank about uniform circular motion. Question number 24. You are on your favorite roller coaster with a diameter of 20 meters. That means your radius is 10 meters. When you're at the top, you feel as if you weigh 1/3 your true weight. So you're at the top of this thing, right? Like that. You're on this little cart, which is probably glued to the track. And you feel, you always have your gravity on you. So your mg, that's your weight. The other thing you have is a normal force on you because you're sitting on the seat of this railway car or this roller coaster car. So you do have this normal force. Your normal force is how you experience your mass on Earth, and normally your normal force is always mg. So you just feel like you weigh, your mass times the acceleration due to gravity. But this question says that that's not the case. You are apparently feeling a lot less heavy at the top of this thing. And so your normal force is 1/3 mg. And those are the only 2 forces on you. Those have to equal your mass times your acceleration. So if you take these 2 forces, and I'll choose a direction for my my axis, I'm going to choose down to be positive just because that's the direction of the acceleration. And so if I'm going to add up all my forces here, Newton's second law, I'll say that mg subtract 1/3 mg will have to equal my mass times my centripetal acceleration. And so the masses cancel, which is important. It doesn't matter how much you weigh on the roller coaster. Skinnier people don't feel way lighter than a heavier person would feel. That would be unrealistic. So, okay, so I got g minus 1/3 g. That is 2/3 g, if you know how to subtract fractions. And that's going to equal your acceleration. Centripetal acceleration is just v squared over r. I'm going to bring this r up. I'm actually trying to solve for v in question 24. So I get 2/3 gr equals v squared, or the square root of 2/3 g times r equals v. And you can figure out what that velocity needs to be. All right, great. That is question 24. Where's my little pen here? I'm going to go to next page. Next question is, let me just check. Next question is number 28. The classic question, we've all had this experience in our life, where we have a jewelry box in our room on a rotating shelf in a mechanical display case. Very true to life question here. Something you can, solve at a party to impress your friends. They tell you the radius is 0.5 meters, and they want to know the centripetal force. Basically, what's the acceleration on this thing? If the frequency is 1 revolution per minute, you'll actually want to change that into revolutions per second, right? So that's got to be 1/60 hertz. It's a smaller number. It moves 1/60th around the circle every second, or once around a circle every minute. So make sure you're careful with that. RPM is revolutions per minute. Our frequency is actually revolutions per second. Great. So what does FCP equal? FCP equals your mass times your centripetal acceleration. What does centripetal acceleration equal? It equals v squared over r, correct? But we don't have a velocity in this question. We actually have a frequency. So I need to change this to the formula 4 pi squared r f squared, like that. And that will get me all the numbers I need. And if I go to find my centripetal acceleration, then it's just mass times 4 pi squared times my radius, which I know, and then times my frequency squared, which is, whatever number you get will be in newtons. And then they want you in question 28 to just, like, part B is switch the frequency to 5. Part B is the frequency is now 5/60 hertz. And part C is the frequency is 0.5/60 hertz. It's easy enough to do that. Okay. I didn't check the answers, but you can obviously check them. If the book doesn't give you the right answer, then the book is wrong. We're right. Next question is question number 36, which says there's a car with a heavy mass. It is 1.7 times 10 to the 3 kilograms, or 1,700 kilograms. It's traveling without slipping on a curved road with a radius of curvature of 35 meters. Before the break, we did these questions where we were on these bank turns, going around circles, right? And our car was like slipping off or on the track, and we had all kinds of stuff going on. I'm not going to put a big involved question like that on our test on Monday. It's just too much work for us. We really need to be in the class kind of working on questions like that every day, the 75 minutes a day thing, to really be able to do these kinds of questions consistently. So we're going to definitely stay away from the big bruiser questions like that. If you remember, we had a normal force, we had friction and all that stuff. What else do they give us in this question? So this is an easier question. There's no banking of any turns. It doesn't look like there's any friction. Oh, there is friction, but we got to figure it out. Obviously, there would have to be friction, or else the thing will just slip off the track. Okay, so if I am, if this is my car, right, and he's kind of heading out of the page, okay, and going around in circles, like in and out of the page, right? These would be the forces on them. The normal force here, the gravity here, right? There will be some sort of friction that holds. He'll want to slip off the track this way, to the left, correct? But the friction will have to hold him in like that. So we'll call that our friction. And those are the three forces on this truck or this car. If I do Newton's second law in the x and y direction, I'll do it in the x direction first and then in the y direction. Hopefully you remember how to do all this stuff. I'll say that y is up and x is to the right. And so I only have one force in my x direction. It's the force of friction. I have two forces in my y direction. I have a normal force and I have a negative gravity. Those need to total 0 so that the force in the y direction is balanced, meaning, the car is not accelerating in the y direction at all. It's just staying on the road. Makes sense. And then in the x direction, I only have one force as well, and that is my mass of my car times my centripetal acceleration, which is towards the center of my circle, right? And so there you go. If I take the equation in the x direction, and I get the force of friction, it's going to equal the force of static friction. Wait, what do they ask in this question? Number 36. Calculate the frictional force between the road and the tires. So I don't even need to deal with coefficients of friction or anything like that. I just need to solve for FF. And so I don't even actually care about what happens in my y direction. But it's good that we wrote it out anyways. So FF is then just going to equal MACP. And I know my M, I know my V squared, and I know my R, and then I could just solve for the friction that's holding that thing on. If they ask for the frictional constant, I would need to solve for a normal force first and all that stuff. But the question doesn't appear to ask for that, so it's a little bit easier to deal with. Okay, question number 47. Number 47. Sorry if my kids are loud in the background. They're like that all day. I'm just going to write down what they give me in this question first, which is they give me a radius, and that's it. They give me some sort of static friction too. I'm going to write that down. US equals 0.4. And it says basically you're pinned up against the wall of something that's spinning. So there's you, okay? And you're spinning around and around and around in some sort of, carnival ride thingy, Gravitron thing. You're touching the wall of the thing, but your feet aren't on the ground. It basically holds you, pins you against the wall. So our free body diagram will be on this person, and here's the forces that will be on them. They will have a mass times a gravity. They will have a normal force, but the normal force is counterintuitive to what we've always learned about normal force, which is just opposite to gravity. But no, normal force in this case is this way. And it's because this person is touching the surface of the wall here, and normal force is always perpendicular to the surface that something touches. So we don't actually have a normal force up and down anymore. We have this weird normal force that is coming from the person getting pinned against the wall. So there's the force there. And then we also have friction here, which is weirdly enough in this direction. And that's because friction is always in the opposite direction the person wants to move. And if we're just looking at this person for a split second, like this split frame right now, they would want to slide down the wall, right? They would want, the gravity is trying to pull them down. And so friction is in the opposite direction that it's pulling down. So I'm going to make an axis X here. I'm going to make a Y direction axis there. And I'm going to add up all my forces here. So in the X direction, I only have one force. I have this normal force. And that has to equal MACP, mass times acceleration. In this case, this person is spinning uniformly around this circle, so they will have a mass times centripetal acceleration. In the y direction, I will have this frictional force, and then I'll have subtract mg, and that equals 0. So those have to balance out. And let's look at this equation first. Fn, which is this. It's static friction, by the way, because, or this is, yeah, Fn is just going to, sorry, let me erase that for a second. So I need Fn equals mv squared over r, correct? And what's the question going to ask me? Draw free body diagram. What force? Calculate the minimum speed. Part B. I don't really care. I already drew the free body diagram. Calculate B says the minimum speed to keep the person stuck to the wall. So that's what I'm trying to find is v squared. I don't know Fn though. And I don't know mass. And I do know radius. So there's my first equation there from the x direction. From the y direction, I'm going to get force of friction, which is mu s Fn minus mg equals 0. It's static friction because when I'm looking at this little snapshot, the person is not moving. Yes, they're spinning uniformly around the circle, but I'm concerned about the free body diagram or the point of view of the person. They're just, if the windows were shut in that thing, they would be pinned to that wall and they wouldn't be moving in their frame of reference. Okay, so there's my two equations. I've got basically two equations, two unknowns, right? I'm just going to take this y equation here and replace Fn with mv squared over r. So I'm going to get mu s mv squared over r. And I'll just say that that equals mg. I'm moving this mg over to the other side of the equal sign. So this is good because my masses cancel out. The mass shouldn't matter. Remember that. And then I could solve for v. It's going to equal gr over mu s square rooted. So there's a nice tight formula for you to solve the velocity that will keep that person stuck to the wall. Okay, so if you've ever been on those rides, they're pretty cool. You can definitely YouTube, you know, Gravitron or Gravitron. I can't remember what the name of that ride is, but definitely interesting to be stuck to the wall of that thing. It actually makes you pretty sick when you get out of it because there's usually someone in the center controlling the ride, and you're just watching, you're just spinning around them, so you get pretty sick pretty quick. Not a big fan of those. I don't think they're around anymore anyways, unless you go to a weird carnival or something. Question 53. A space station is rotating at 12 meters per second, so V equals 12 meters per second. And the gravity is equal to 50% of what the Earth's gravity normally is, which means that the normal force that someone is experiencing is 0.5 times their mass times the Earth's gravity, right? That's the 9.8 there. And they want to know the radius of the thing, the spaceship that's spinning. So if this person is here, there's your person, okay? They'll have a normal force here like that, and that's the only force that'll actually be on them. They're nowhere near any bodies of mass, so there is no gravity on them. But this ship is spinning, whatever direction it spins in. So the force, the normal force they're experiencing is equal to MACP like that. And so we said that this is 0.5 times mg, and that's equal to mv squared over r. The masses will cancel, which is good, and I'm trying to find r, so I will say that r is equal to v squared over 0.5 g, like that, just bringing this down, swapping with the r. and that will give you the radius of the spaceship. Okay, those questions are actually quite easy once you get the idea of what they're asking. Let's see. Now we're on to the gravity questions from page 315. So quickly take those up. There's some really cool questions that we would have done if we were in class, but we're just going to stick to the basic stuff again. I wanted to talk about like geosynchronous orbit, where that's where, you know, a satellite basically hovers over the same spot on the Earth at all times if it's the exact right distance above the Earth at the exact right speed. But I guess we'll have to skip that for now. Number 52, a satellite in orbit above the Earth's equator is traveling at an orbital speed of this: 7,450 meters per second. The speeds are really fast in these questions because in order to basically travel in orbit around the Earth, you have to be going really, really fast, obviously, or else you could just get in a car and fly off the Earth. It's just not yet happened to anybody as far as I know. Okay. You can look up videos about Mad Mike, that guy who went up in the rocket to discover the Earth was flat. I'm going to give you a spoiler alert. He didn't make it. All right. Determine the altitude of the satellite if it's in orbit above the Earth's equator, is traveling at an orbital speed of 7.45 kilometers per second. So they want the orbit and they want the radius and they want the speed. So what's the formula here? Let me just draw a picture first. Okay, here's my little satellite up there. It's the only force on it here, right, is the mass. Okay, so the force between two objects, we talked about the gravitational field on something, right, is the mass of the satellite, and then that's times this big G times the mass of the Earth, right, divided by the radius squared. So that's going to be the force on this satellite from the Earth due to the gravity. And then this force is going to have to equal the mass of the satellite times the centripetal acceleration of the satellite. So the formula we're going to get is msg times the mass of the Earth divided by the radius squared equals the mass of the satellite times v squared over the radius. And so when I can cancel the mass of the satellite, it doesn't matter what the mass of the satellite is. It matters what the mass of the Earth is, because that's what's supplying all that gravitational field strength, all the force that's pulling that satellite towards it. And I have to solve for the radius, right? I have to solve for r. Is that what the question's asking? Let me just look at number 52. Yes. Calculate the altitude, which is essentially the r. So I guess I'll bring this r up here like that. And so this will just equal r, because those r's will cancel. And then I'll bring this v squared, I'll swap it. So I'll get gm of the Earth over v squared. Now that'll give me the radius of how far I am from the center of the Earth. So the final answer, the altitude will just equal r subtract the radius of the Earth, because, you know, what I found was this distance, this is my satellite, this is my Earth, and that's r, but I actually need like this little altitude here. Hopefully that's not too awkward to see. Okay. And if you want to find the period, then it's easy enough to do. Where's my pen? The period is just going to equal 2 pi r over the velocity. You know the r, you know the velocity, and you can find the period in seconds. And you can see how long it takes the thing to go around the Earth once. Probably not that long. It's usually on the scale of minutes or hours or something. Good, good. Question number 54 says Neptune has an orbital radius from the sun of this. Now, I don't know, they gave it to us in kilometers, so instead of 10 to the 9, I'm going to go 10 to the 12 meters because I don't want it in kilometers. Alright, so I got my radius there. They want the speed, right? And so I got my sun, and I got Neptune, and it's going around this thing in a circle, and what is the force that's going to pull this thing in? It's going to be that gravitational force. So the centripetal acceleration here is going to equal this big G times the mass of the sun divided by the radius squared. And I'm looking for V, right? Calculate the orbital speed. So I'm just going to say V squared over R equals G times the mass of the sun. Now, it doesn't really matter what the mass of Neptune is. So it just matters how far away it is, really, from the sun. And so when I solve for V, I'm going to get G times the mass of the sun divided by R. So I bring this R up, and one of them cancels with that one, and that's all square rooted. So you can figure that out. This is a really small number. This is a even way bigger number divided by another big number, square rooted. Find the velocity of Neptune. I'm sure it's really, really fast, right? But I'm sure if you worked out this centripetal acceleration, it would be really, really small, I think. Let's see what the centripetal acceleration is if you're on Neptune, just from spinning around the sun. Let's see if you would even notice that acceleration. So in my calculator, I'm going to times it by G, which is constant 39. The mass of the sun is like 2 times 10 to the 30 kilograms. And then I'm going to divide that by 4.5 to the exponent 12 squared. Yeah, so the number is tiny. But you still end up with a huge, huge speed because you're so far away and you have to go around this really, really big circle like in a certain period. So let me see, how many zeros is that? 5 zeros. Okay, so that is an insignificant acceleration. You would not feel that acceleration, even though it's there holding Venus in the orbit, right? It's insignificant. It would not affect, the gravity on Venus. The G of, Neptune or whatever is probably like on the order of, 12 meters per second squared or something. I'm not sure. You can look it up in a chart, but you're not going to feel this this change in the 100,000th digit, right? But it is there. Same thing with the Earth spinning. We're on this big spinning globe, right? The Earth is spinning. How come we don't feel any acceleration that we're on this spinning thing? And that's just because I think the centripetal acceleration of the Earth spinning is like 0.01 meters per second squared, and the problem is we have this big gravity pulling on us that's 9.8 meters per second. So this is actually like semi-noticeable, but because the Earth's gravity is so much bigger, it's 100 times bigger, we don't notice the fact that we're on this spinning sphere. Okay. All right, last question is number 59. And there's a satellite, Canadian satellite, I guess. Never heard of it. Anik F2. It has a mass of 5,900 kilograms. It orbits 35,000 kilometers above the equator. So with that knowledge, this is the radius of the Earth, right? It's like 371. And how many zeros? Something like that. Meters. That makes sense. Okay, and then that's the radius of the Earth, and then I have to add to it 35,000 kilometers, which is this number. So that's my total radius above the Earth. This thing's way up there. Okay? Because the radius of the Earth is only like 6,400 kilometers, right? And so it's way farther above the Earth than the actual radius of the Earth. Okay, so I need to determine the gravitational field of Earth at this altitude. That's no problem. The gravitational strength of the Earth is just g times the mass of the Earth divided by the radius squared. I'm actually going to do this one on my calculator because I want to know what this radius is first. It's 6371000 plus 3500000. So the radius that this thing is from the center of the Earth is 4137100, 41 million kilometers away. So when I plug all these numbers into my calculator, I'm going to get the mass of the Earth is 5.98 times 10 to the 24 kilograms. You can look that up. If you need that on the quiz, just look it up like you're at home. So you can look up whatever you need, I guess. And then 41,371,000 squared. So here is the gravity of, here's the Earth's gravity pulling on that spaceship. It's a tiny little acceleration, 0.233, but it's still there, right? There's still acceleration outside of the Earth for a long ways out. We just always assume like as soon as you leave the atmosphere, all of a sudden there's no gravity on you, and that's not the case. It's only the case because you're for things that are in orbit around the Earth. Remember that if you're in orbit around the Earth, right, you can only have, if you're orbiting the Earth, then your centripetal acceleration has to match the strength of the field strength of the Earth. And if that's not the case, then you'll fall back to the Earth. And if it's too slow, if you're traveling too slow, you'll fall back to the Earth or fall into a higher orbit. Does that make sense? No. If it's too slow, you'll fall back down. And if it's too fast, you'll fly off of the orbit. So you need this perfect balance between your centripetal acceleration and the gravity that the Earth's exerting on you. So you end up not having it in normal force when you're in there. And that's why you feel weightless. You're essentially just falling around the Earth, right? If you get into this perfect orbit, you'll end up just falling around the Earth forever and ever. It's really pretty boring up there. Okay, determine the gravitational force of the Earth at this altitude. Determine the gravitational force. Part B says what's the actual force on the spaceship, and that's just going to equal the spaceship's mass, 5,900 kilograms, times the acceleration we just found. 233, something like that. Sure. Work that out. It's going to be, 1/5 of this, probably like 1,000 newtons or something. Not very much force, especially on that really heavy thing. Calculate the speed in order to maintain that orbit. Well, the centripetal acceleration is v squared over r, and that has to equal 0.233, so you can then find speed. This question kind of covers everything. And calculate the period as well, so then when you have the speed, it's 2 pi r over v, okay? So there you go, guys. Hopefully that was helpful. Look forward to getting some quizzes back from you on Monday. Try it. It doesn't hurt to try it, so I think it's important. Physics is a really important subject to know going into university. I think it helps you with a lot of the other courses you're taking, especially if you're going into engineering. So it's good to know this stuff, good to practice this stuff, and let me know what you think. All right? We'll talk soon. See ya.